Hello, young physicists. Have you ever wondered what holds the tiny nucleus of an atom together, despite all those positively charged protons trying to push each other away? It turns out there's a super strong but very sneaky force at work, just like your friend's hug that's strong enough to stop a runaway balloon. This force is called the nuclear force, and it acts attractively between nucleons, which means protons and neutrons, inside the atomic nucleus. It's extremely strong enough to overcome the electrostatic repulsion between positively charged protons that normally want to fly apart. Interestingly, this force doesn't care about electric charge. So whether it's proton-proton, neutron-neutron, or proton-neutron pairs, the strength is nearly the same. Now, this force only works over very tiny distances, less than about 2 femtometers or 2 times 10 to the minus 15 meters. Beyond around 3 femtometers, it basically disappears as if it never existed, and it reaches its maximum strength roughly at 1 femtometer separation. To describe how this force varies with distance, physicists use what's called the Yukawa potential. Imagine it as an equation that looks like a decaying exponential divided by the distance, specifically v of r equals minus g squared times e to the power of minus mu times r all over r. Here, mu relates to the mass of a particle called a pion, the messenger of this force. Another fascinating feature: the nuclear force is non-central, meaning it depends not only on how far apart the nucleons are but also on their spins and how they're oriented in space. This spin dependence brings in what are called tensor components, which play a critical role in binding the deuteron, that famous proton-neutron pair, and create interesting spin effects in bigger nuclei. So, this isn't just any force, it's a short-range, super strong, and spin-sensitive connection that keeps the very heart of all matter stable. Cool, isn't it? Alright, let's peek behind the scenes and see how we actually know that this nuclear force exists. Scientists deduced its presence primarily by studying the deuteron, which is a bound system of a proton and a neutron, and by looking carefully at neutron-proton scattering experiments at low energies. The deuteron isn't just casually stuck together, it has a binding energy of about 2.2 megaelectronvolts, which tells us there must be a very strong attractive force holding these nucleons tightly enough to beat the repulsive Coulomb force between the protons' positive charge. Now here's a fun fact: the deuteron has a spin of 1, meaning the spins of the proton and neutron are aligned, like two little magnets pointing the same way. Also, there are no excited states of the deuteron, which hints that the nuclear force isn't a simple, central force but has a tensor component that depends on spin orientation. When physicists measure the differential scattering cross-section, that's how the scattering intensity changes with angle theta, it shows a clear angular dependence. This pattern is modeled using effective nuclear potentials, capturing the force's complexity. The scattering data further reveals that nuclear potentials have something like a hard core, a strong repulsive center at very close distances, and an attractive tail. Imagine a tiny nucleus guarded by a strict bouncer. All this combined experimental evidence paints a consistent picture of a strong, short-range, spin-sensitive nuclear interaction. That's how clever experiments tell us stories about what we can't see directly. Now, time for a little story from the 1930s. Hideki Yukawa, a brilliant physicist, suggested something quite revolutionary: that the nuclear force arises from the exchange of virtual mesons, specifically pions, between nucleons. Think of these pions as messengers carrying the strong force back and forth, much like tennis balls exchanged between players across a net keep them interacting. Yukawa proposed that because these mesons have mass, the nuclear force must have a limited range, inversely proportional to the meson's mass. Mathematically, the range r is approximately the reduced Planck constant divided by the pion mass times the speed of light, that is, R equals h bar divided by m pi c. The beauty of Yukawa's theory is how it models nuclear interaction with that same Yukawa potential we talked about. V of R equals minus g squared times e to the power minus mu r divided by r, where mu equals m pi c over h bar. This theory elegantly explains why the nuclear force is so short-range yet so strong, tying together fundamental constants like g squared, the coupling constant. Since pions have masses around 140 megaelectronvolts, this leads us to a force range of about 1.4 femtometers, perfectly matching what experiments show. Yukawa's insight was like lifting a curtain, revealing how Meson exchange underpins the nuclear force, just like photons mediate electromagnetic force. Quite the eureka moment, right? Let's apply what we learned with a quick example. Suppose we want to estimate the approximate range of the nuclear force using Yukawa's idea. Given that the pion mass is about 135 megaelectronvolts divided by c squared, our target is to find R, the range of the force. From Yukawa theory, we know that the range R equals the reduced Planck constant h bar divided by the pion mass times the speed of light. That's R equals h bar over m pi c. Now, substituting the numbers, h bar times c is approximately 197 megaelectronvolts times femtometers divided by 135 megaelectronvolts. Doing the math, we get R equals 1.46 femtometers. This result aligns beautifully with the empirically known range of strong nuclear interaction, which lies between 1 and 2 femtometers. So, this simple calculation based on fundamental constants gives us a neat way to see why the nuclear force is limited to such tiny distances. See? Physics formulas aren't just scribbles, they tell precise stories. To wrap up, let's recap the magic formula and key points for nuclear force. The potential energy that governs the nuclear force is given by V of R equals minus g squared times e to the power of minus nu times r divided by r. Here, nu is the pion mass times the speed of light divided by the reduced Planck constant. The range R of the nuclear force is expressed as the reduced Planck constant divided by the pion mass times the speed of light. What does this mean in simpler terms? The nuclear force is the strongest of all fundamental forces at play inside the nucleus, but it operates only over tiny distances less than about 3 femtometers. It is charge independent, so it affects protons and neutrons almost equally, and it's spin dependent, meaning the nucleons spins matter a lot. Another interesting feature is saturation. Each nucleon feels the force mostly from just a few nearby nucleons, not from the whole nucleus, which keeps things balanced. Yukawa's Meson exchange theory elegantly ties all this together by linking the force range to the mass of the mesons that mediate it, explaining why the nuclear force is both short-range and powerful. So, the secret of nuclear stability lies in this finely tuned, strong but short-lived handshake between nucleons. That is it for today's concept. Remember, physics is fun when you can laugh and learn at the same time. See you in the next session, where we dive deeper into the heart of the atom.